Hello, everybody. Please let me introduce myself. My name is Marco Orellana. I am CIDAI's manager. As you know, CIDAI is a key element for the Catalonia AI strategy. Our mission is to demonstrate the advantage and speed up the adoption of innovative data exploitation and artificial intelligence technology, with the visions to promote the Catalan ecosystem to become an international reference in this area. We are working in several tasks to increase the adoption in this technology in the territory. I invite you to have a look of our website to know better about CIDAI's proof of concept, studies, project, among others. Today, one of the partners of CIDAI, Fundació I2CAT, will lead this session, AI for Future 6G System. In this masterclass, we will review AI technology expected to shape future on 6G networks. Before to introduce our speaker, if you work in a SME and you have ideas to develop some proof of concept with AI technology, please visit the project EU Hate for Data, FF for Euro HPC, IoT Engine, and Terminate. Here you will find some interesting financing opportunities. So, let me introduce you Xavier Costa. He's an ICREA research professor, a scientific director in Fundació I2CAT. Please, Xavier, the floor is yours.
Thank you very much, Marco. Okay, so it's working fine. Everyone can hear me, see me. Anna, can I go ahead?
Yeah, perfect.
Okay, then welcome everyone. Thanks a lot, Marco, for the nice introduction. The talk today will be about artificial intelligence for future 6G systems. So let's start. First thing I have today is let's look at, if we're talking about 6G, what is 5G and where are we? So here I have a graph from Gartner, which is a consultant company, where they show basically different technologies in terms of their evolution through time and the expectations that they raise during their lifetime. So here, first we start with an innovation trigger when people start talking about certain technologies. Here you can see augmented reality, you can see transfer learning, you can see knowledge graphs, and of course you also see 5G, we'll be talking about that. And after some terms get popular and they start getting some research, we go through what is called the peak of inflated expectations. After a while, when we say that, okay, we will solve everything with this new technology, there is a slowdown phase, which is called the through of disillusionment, which basically means that we start realizing that maybe we cannot solve everything with this wonderful new technology. And eventually we get to a convergence period where we say, okay, we cannot do everything, but we can do several things. So 5G, as I mentioned, it's here. It's basically at the peak, but already going down in terms of, okay, we can do everything with 5G. The reasons for that is, okay, we already have a 5G standard by 3GPP, so we already can do products with that. We already have first operators that are offering in the world 5G communication, so we can already test what it means and what it offers. Then it's already being deployed in major cities, so we start getting into some steady period, and the technology is supposed to be, let's say, fully deployed everywhere in 2 to 5 years. In 2 to 5 years, everyone is expected to have a 5G mobile phone or even a car that is connected with 5G. So if we remember when we started talking years ago about 5G and which promises we had, what we said is, so far with 2G, 3G, 4G, what we did basically was to connect more and more people first with the mobile phones, then we had even houses connected, then maybe some industries, and at some point of time, because it was mainly limited by the amount of people that were having devices, there was basically a saturation point where the number of devices in the society was reaching a maximum point, because at some point of time people might have one mobile phone, they might even have two mobile phones, but there is a point where you don't need more mobile phones anymore. The main change with 5G is basically that it's meant to enable the digital transformation, right? Which means with some new technologies I will be talking about, like virtualization, like network slicing, 5G is supposed to, let's say, not connect people anymore, but to connect, for example, cars. So every car could be connected and we could get access to new services, advanced services that we didn't have before. Logistics, like many industries in transportation will benefit from having connected services. The same for factories, e-health, public safety. So there are more and more situations where we use cameras and where these cameras can be connected through cellular to help in public safety situations. Banking, more and more we are using our mobile phones as well for doing transactions. And in this case, we need new services, new facilities there. And in general, the smart cities are certainly a target for this. So in order to enable that, what we said is we will have basically, I'm just trying to put better my setup, one moment. We will basically have peak data rates, what will be like gigabits per second. We can have latencies which enable much faster response times in the order of milliseconds. And then this will mean that, for example, when we are in high-speed trains, we should be still supporting higher speeds. So if before, according to the standards with 4G, we could support 350 kilometers per hour, then maybe now with the high-speed trains between many cities, we would like to support 500 kilometers per hour. We will have much more connection density, meaning there will be many more devices per square kilometer. So for example, in a city, in a big shopping center, in a big train station, in a big sports event, we are supposed to basically provide much better services there. And also in terms of network energy efficiency, so due to climate change, due to the decarbonization new regulations, the network is one of the main contributors to energy consumption, and therefore our network should become more and more efficient. So here, one of the issues, of course, is all these additional new kind of KPIs. So having more data rates, having lower latency, supporting more connection density is not something that we want to have everywhere, right? We don't want to support 500 kilometers per hour connections if you are not in the path of a train, because according to regulations, we are not supposed to drive that fast. We don't need to have support for very high connection density everywhere. Like if you're hiking in the forest, probably you don't need to have, you are not expected to have so many devices around, while if you're in a train station, that should be the case, or it's expected to be the case, etc. One of the reasons for that is that supporting these extreme KPIs, it has a very high cost. So we cannot just provide it everywhere, especially if it not be, we will not be getting any reward out of that. So next thing that we had to do was to look at the different, what it's called industry verticals, like factories, automotive, energy, e-health, and basically check which are their actual requirements and in which places this is needed. So as an example of what we have been doing in this space with 5G so far, we had projects like, in this case, I will be presenting the 5G transformer, where I was the technical manager of this large European project, where we had multiple verticals. In this case, we had, for example, the Madrid emergency services, the ambulance emergency services, for representing the e-health vertical. We had Chrysler Fiat for representing automotive vertical. We had Atos for representing the media and entertainment, as they are basically offering the broadcasting services for the Olympics. And of course, we had also operators, which on top of their usual services, they might want to offer MVNO services, which means a specialized service maybe for gaming, for trading, for different users. So what you see here in this picture is that at the lower part, we have our infrastructure, so our mobile network, which might even have multiple administrative domains. So think about, for example, when you cross a border, in one side you might have an operator, in the other side you might have another operator. And then for each one of these verticals with different requirements, we want to have a network that satisfies what they need. So with different colors, you see that green was used for the operators, light blue was used for e-health, red for automotive, and kind of lila for entertainment. What we are representing here is what I will be referring to in the future as network slicing, where we basically have a physical network. And in 5G, we have a new thing which is called network slicing, where we can create virtual networks on top of this physical infrastructure with different properties. One might have more data rate, one might have more better latency, one might have some more computing. So what we are doing is from the verticals, through an element that we call vertical slicer, we get the requirements for the network slice, the kind of network services they will require. Then a service orchestrator will basically create these network slices automatically, and this gets translated into the real network. So as an example of the kind of advanced services that we were looking at in this project, what you see here is an automotive proof of concept where we looked at an intersection use case. So the main issue here is when you have intersections is one of the places where you have more collisions. And with 5G services, if most of the cars are connected, given that we know the position, we know the movement, we can basically predict in real time the probability of having a collision in an intersection and hopefully warn the drivers. So here what we had is multiple vehicles that are sending information to the network about their location, their speed, and all sensor information that is available. Then in the network, once we reach the base station, we get to the network and to the mobile core. We had at the mobile edge computing side different building blocks to basically process information, and with this extended virtual sensing service, predict basically whether we expected that there will be a collision. If that will be the case, what we do is for the cars that we expect that might be involved in this collision, we can go back. This is what you see here as vehicle 2, and tell them that we expect a collision. Please to slow down and try to stop the car to avoid that. Of course, this is something that you can do, let's say, with easy mathematics. You can compute, given the speed, given the direction, whether you expect that two cars will collide. You can also take the information of the traffic lights, also to see whether it's anyway not happening because that will be a traffic light. You can see if people are not respecting the traffic light, so this could also have an effect on that. And when you start putting all this information together, you can basically build a model to learn whether your predictions are good and also improve these situations. So at the end of the day, as I said, what we want to do is to avoid collisions. I guess everyone agrees here that this will be something that people would like to avoid when you're driving or even as a pedestrian. And then we're basically through the 5G connections providing a warning message to the drivers where we could even trigger an emergency braking. This was done, as I said, with the research center of Fiat Chrysler. They have an intersection trial area for proof of concepts that is represented here. So we were driving here with multiple cars in this intersection that you see depicted. And basically we were trying with a driver inside to make the cars collide and trigger this prediction system to enable an emergency braking system that we also incorporated into the cars. What you see here is the car that we used and some of the people that were involved in this experiment. And this was the car where I was driving in. If you look carefully, you might even find my picture there. And it worked perfectly, so we are still alive. Another example, as I said, for 5G and what we promised and what we have been trying as advanced services was with SAMUR, with the ambulance emergency services. In this case, the requirements that we got from SAMUR was that currently most of the operations are still manual, so they need to get a phone call, they need to talk to the drivers, they need to give indications by voice, and in many cases, even when they reach the place, because the people is inside a building or in a difficult to reach place, they have problems to find a person. The main criteria that they have in ambulance services is the time since they receive a phone call or the alert until the time that they have a doctor checking the person that was injured. So this is the main target that we were trying to minimize here or to reduce. So how do we want to have emergency systems in the future? In this case, what they told us is they would like to have, in the case of patients at risk, they wanted to have smart devices like a smartwatch that is checking the heart rate beatings, and through some machine learning detect, given the place where a person is, given the sensor information, the health information they get through these smartwatches, whether they should start preparing for a potential emergency. This could save them some time. Next thing is they would like to avoid having the person or some witness around taking the phone and calling the emergency services. So ideally, they wanted to have this smartwatch directly realizing that there was an emergency, since it had the location, since it had connectivity, inform directly an emergency system. There is this person that is having maybe a heart attack in this location, please send an ambulance there, right? In addition to that, once the doctors are going there, they will like in the ambulance or through, in this case, we use augmented reality, that the doctors have the information regarding which is your blood type, whether you had any previous disease, any information that might be relevant for this case. So this is something that could also be delivered here. Here you have an example of how the glasses were looking like for augmented reality. This is a real first responder from SAMUR. Here you see that we basically simulated an emergency inside a building, in a basketball court, in a school, and how basically in the right side of the picture, how we could collect the data regarding this patient, and it was displayed directly into the glasses of the doctor. So with that, I think we can go to the first video, Anna.
Anna, do you have the video?
Just a moment.
Nowadays, in order to respond to an emergency, a human witness is first required, who must call 112 and describe what has happened and where. This call is processed by another human being, who must quickly decide what is the emergency, how severe, and which is the best team to be deployed. The team must be able to reach the location of the emergency and provide the best possible treatment. All of this will dramatically change thanks to 5G. The 5G Transformer European project has designed a 5G communications architecture capable of adapting to the specific needs of different verticals. The project addresses use cases related to automotive, media and entertainment, mobile virtual network operators, Industry 4.0, and e-health. Milan is playing basketball. He wears a smartwatch connected to 5G, capable of monitoring different medical and environmental parameters, which are periodically and safely sent to a central medical server in the cloud. This server is capable of predicting or detecting a health issue, for example, a heart attack. This monitoring is possible thanks to the capabilities of 5G in terms of MMTC and low energy consumption, enabling an automatic detection of emergency situations without any type of human involvement. If the system detects an accident, it locates and automatically sends the emergency response team that is better suited to deal with a specific emergency and closer to its location. Thanks to the use of artificial intelligence techniques, it will be possible to better decide what type of response is required, again without human intervention. The person that suffered the accident is automatically contacted by the system to determine if it is a false alarm. While the emergency team arrives to the location of the accident, 5G network automatically deploys the resources needed to provide an advanced and personalized treatment to the patient. The 5G EMBB and URLLC capabilities and its tremendous flexibility enable that the needed resources are deployed closer to the emergency location, making possible the provision of augmented reality AR services to the emergency response team. The use of AR enables features that were impossible before. For example, the medical team is guided towards the exact location of the patient, thanks to the use of AR goggles. The emergency team arrive to the location of the emergency and start treating the patient. The AR goggles allow the doctor to visualize information in real time about different medical parameters, for example, blood analytics or heart rate, as well as to send a video feed to a specialized medical team providing remote support. This will drastically improve the decision-taking process of the medical personnel, showing the most relevant information at any time. This novel technology was shown live in November 2019 to a group of mobile network operators, vendors, public and private health-related companies, and government authorities, with great success.
Okay, so this was an example of what we did here with 5G. So far we have talked about 5G, what was promised and showed what was achieved. So far, of course, you don't see this in reality, but in research, we already need to look at what will be next. So if we look at what is going to be next, of course, we are engineers, so we are not very, let's say, creative. So after the 5 comes the 6. So we are looking at what will be the 6G technologies. In terms of what can we offer new, if before we were promising gigabit data rates, now we are promising, of course, terabits per second. If before we were promising 1 millisecond of latency, now we are promising 0.1 milliseconds. In terms of density, more density and better positioning. So this is pretty much what it's called faster horses. So every time I give you a bit more speed, I give you a bit more data rate, and hopefully any creative people in the world will find very good ways of using that. If we look more on how this might affect society in general, what we see is that we are moving more and more into having a fully connected society, right? So having from the physical world, so it means machines, it means objects, the human world, so it means the persons, the lives that we have in the world. How can we basically have more and more information about this physical and human world into a digital world? So that's that we have better and better picture of the world in the digital dimension, which is usually called a digital twin. So trying to have a digital twin of as many objects and as many humans as possible. So in general, if you think about autonomous driving, most of you with 5G still, you will not have a self-driving car. So you might have a car that is able to turn already, that it's able to brake. So towards 6G, we are hopefully expecting that you will be, once Corona is not there anymore or it's under control, you will be commuting at least sometimes to your job, and hopefully you can read a book or do something else while doing that. Also during the pandemic, we have seen a lot the need for having more and more connected industries. So basically trying to be able to, in future pandemics, to operate factories, to operate logistics in a way that we don't need so much the human interactions, at least that it's not mandatory to keep things going. So the question is, how do we get there? What do we do new here? And how does artificial intelligence helps us to get there? So the first technology that I wanted to present to you where artificial intelligence plays a major role, it's called wireless sensing. So let me explain what do I mean by wireless sensing. As you know, when you have a mobile phone, when you have Wi-Fi at home, signals, the cellular communications, the wireless signals can travel through walls. And what some research has shown is that actually it provides a lot of information about the environment, about things that are not visible because they are behind walls, also about objects and materials. But of course, this is a bit difficult to find. So how do we do that? How do we actually harness this information? In this case, artificial intelligence is especially suited for interpreting the radio frequencies or RF reflections. This has many applications for e-health, public safety, security, and it's a new area, so we will be finding many more. And here, Anna, if you can send the second video, you will see an example of how this is actually working in practice in the laboratories at the moment. Thank you, Anna. So what you have seen here is an example of how wireless signals can be used to see through walls, in this case, through objects, and how, in this case, they could be used to actually follow the skeletons and even more attributes of people in such scenarios. Here I can show you, besides what we have seen, what is behind the walls. One of the areas that is being studied at the moment is whether we can even recognize different parts of the body, so the feet, the arms, the chest, the head. This is all done by using signal frequencies, specialized signal frequencies in buildings, and then trying to reproduce, reconstruct with an algorithm, with a machine learning algorithm, what these reflections means and whether they can be attributed with a certain confidence to people in this case. Applications of this, as I was mentioning before, for e-health, they are very clear. If you have someone at home that maybe you need to monitor because they might fall, they are ill, they are old, you can, as you can see here, you can see in which area the people are located, whether they have been moving, even whether the movement was normal. And based on that, you can also take decisions, right, on whether you should send someone, you should send a doctor to this place, whether maybe someone has fallen down and will need some assistance. Of course, there are many other applications like this. So if someone works in public safety, if someone works in military, there are many other applications that you can do with that. Which is the problem of this system so far, as I mentioned, from different universities. The problem is that it's a specialized system, right? So you need to deploy devices into a building, into a home, in order to collect this information. So some research that we have been doing in my group for a while has been, okay, let's imagine actually that we have devices at home that are anyway creating radio signals. So in this case, probably every one of you has some Wi-Fi access points at home, and these Wi-Fi access points, they are basically radiating signals, and these signals could actually be used also for this purpose. So in this case, the normal frequencies that we use, the normal devices that we use, maybe they will not be suitable, but in the future there will be millimeter wave, which is what we are using here. It's already available commercially, which are working at the higher frequencies, and they have a much more narrower beams. So here you can see our office. where we deployed 4 access points as you have in the picture, which are commercial access points that you could buy for getting Wi-Fi connectivity in your home. And we created a human phantom. In this case, you see these barrels that are stacked one on top of each other. We used to call this in a friendly manner Bob, and we were moving Bob through the room in these reference squares to see whether we could detect persons and the position of the person inside the room. So in this case, of course, Bob, these barrels were filled with water. So this is one of the main representations for signals. When signals bounce back in people, one of the easiest characteristics to pick with machine learning is the reflection into water, because it's our body is full of water. And here you can see the results. This has been published in some conferences. I just add here some references. I will be doing that later as well, in case you want to look into the details. But this is basically the map of the office that you see in the picture, the position of the access points and the stations, and how we could detect the position of Bob, of these barrels of water, in the different places in the office. This, of course, has, again, many applications, as I said, in e-health. And now with Corona, of course, also to see whether people are keeping distance or not. And also in outdoors, right? You see, for example, these are some news from Barcelona, where the town hall was deploying some cameras and they were doing machine learning on the video feeds to find out whether people were following the rules, whether there was too much people by the beach. In this case, this technology will allow to do that without all the privacy concerns that having cameras outside have. So people sometimes they don't want to be seeing the cameras. They don't know what will happen with the video feed later, who will get access to that. So in this case, since we are just counting bodies and how the radio signals are bouncing back from the bodies, this is much more privacy preserving. So how did we do that? As I said, we had these 4 access points. We had this room where we were dividing it into squares and finding out in which places these barrels of water were located. And what we did here for machine learning was basically first we built a model of the environment. So we had the reference environment where certain propagation statistics that we could see from these devices, from these millimeter wave devices. We started in a state which was, of course, we don't have any intrusion. And then we were looking for outliers. So whenever there was a major change in the propagation statistics, we basically developed a model to see whether it was above a certain threshold. And then in the case that an outlier was detected, then we had to analyze whether the intrusion was something that was that we believe it was real, or whether it was just an artifact and we didn't have to look into that. We also had to add another state here, as you see, the similarity check, because of course when someone moves into a place, it changes our reference, but after a while, if we are taking more measurements, this will become our reference again, right? So we had to basically keep some memory and check with the similarity check module whether we were still with each other inside in our premises, or whether it was gone already. Here we used basically as input the signals that we received in the time dimension for the different links that we had in the system. So for each one of these access points and stations, we could establish 1, 2, 3 links, and we could analyze the data that we had from this scenario. And we had a convolutional layer to reduce the space because it was very large. and then a simple neural network to basically first have a fully connected layer to process information, and second, decide whether it was classified as an intrusion or not, the event that we saw. And the result that we had here was for a certain measurement window. So if we were giving enough time the system in terms of seconds to check the environment, we had for one active link, we were reaching detection accuracies of about 92–95%. With 2 active links, we were jumping a lot and going already close to 98–99, and with 3 links, we were already reaching the top, so we didn't need to add additional links. So this was one example of how in the future we can have devices that you have to think, we call this passive because actually we let the access points, the Wi-Fi access points you will have in your home, just do their normal operation, and we just have access to the measurements they usually do to align the beams to see how to get the best connection. And with this information, we could derive whether there will be a person or not, and which position, whether there was movement inside a room. So this was to illustrate the potential of wireless sensing inside buildings, but there are also many applications outside, right? So in the case of the public safety, when you are looking for someone that has been lost hiking, for example, the typical application that you will see is you can send in the future a drone with a camera. This camera might have infrared cameras. These drones might have also cameras that can analyze the images to see whether it's the shape of a person or even some object that we are looking for. But this, of course, has some problems. What happens when you're looking for a person, but this person has been lost in a forest, which is very difficult to reach with cameras, with infrared cameras, with computer vision? What happens if you're below snow? What happens if you're below rubble because there was an earthquake? So here what we did was for future systems, on top of having a drone that has an infrared camera, on top of having a drone that has computer vision and is processing the video feeds that we have, we could also make use of the fact that when everyone is hiking, one of the things that they have in their hands is a mobile phone for doing very useful things like taking selfies on the way. And these mobile phones can actually be very useful in terms of finding people when they are lost. So here, let me show you an example of what we did in our team, where we took a commercial drone and we basically fitted a computing platform, so in this case an Intel NUC. We also had a software-defined radio, in this case a user B210, where we installed 5G communications, in this case 4G, sorry. We had antennas, we had the GPS, and basically we wanted to use this drone to see whether we could do wireless sensing of lost people through their mobile phones, right? So in this case, the idea is we have a drone that is flying around with a mobile phone base station. This base station is basically advertising itself as a normal base station, like if it will be your regular operator. And when the mobile phones that are in the area respond to that, providing some response messages, we are measuring what it's called the time of flight duration to actually locate where this mobile phone might be located, right? In traditional localization solutions, what will happen here is that you will need to have 3 base stations and take different measurements from these base stations to do trilateration. The advantage that we have with a drone, if we only have one with a base station on top, is that we can actually move the drone and based on that take different measurements as if it will be different base stations, right? We even have control on the drone and we can improve things. So here what we did was to take this time of flight measurements and start applying a pseudo trilateration, as we call it, technology to, based on the time of flights and the different channels that we see in the different positions, filter that in order to, through a 2D convolutional neural network, process where do we think that the position of this mobile phone could be. This was basically to approximate the location of a person, but this person could also be moving, right? In the case that someone is hiking, is lost, but maybe the person is trying to find a way back, this person will be moving. So we have this green block here that you see as an encoder-decoder long short-term memory, where what we were doing there is taking the predictions of the locations that we had, pass it through this module to see whether there were major changes in our prediction that where we could basically predict the new position and move the drone, the UAV, accordingly in order to basically minimize the error in localizing this person or even giving to first responders the localization, the direction where this person might be moving. Here you have a picture of some field trials that we did, and we have, again, a couple of papers describing what we did here, and a video where you can see an example of that. Anna, if you can start the next video. So thank you, Anna. Let's go back to the presentation.
Ya la estás mostrando, pero no en pantalla completa. Ahora, perfecto.
Okay, so I see we are already at more than half of the time, so maybe it's a good time, Marco, to see whether there is any question from the audience so far.
Yeah, perfect. Here we have one question, Xavier. So far, we have mobile network without any AI-based operation management. Do you think that it will be a must in the future, or some operator will do well without any AI?
Okay. So I think, as I said before, since we are basically using networks, mobile networks for more and more applications and more industries like automotive, public safety, health, smart cities are adding more and more requirements to the mobile networks. Once we have these network slices per industry vertical, per application that we want to fulfill all at once, the feedback I get from talking to people managing these networks is that this will be way too complex. So we already have plans to manage this with human operation. We usually take between 2 and 6 hours to find problems to resolve them. So in my view, I expect that machine learning, artificial intelligence will be needed in order to prevent having these problems and to resolve them much faster, because otherwise it's not scalable with humans. All these parameters, all these new things that we need to manage, it's getting too complex for current systems.
If you, the audience has more questions, you can do it here in the right part of this webinar. And then we will ask this question to Xavier. Xavier, we don't have any more questions right now. If you want, we can continue.
Okay, then I continue. Thank you, Marco. Do you see my slides well?
Yes, it's okay.
Okay, I see myself. One moment. I can move it.
We can see the presentation.
Perfect. Then next thing I wanted to talk about today, where I think artificial intelligence will play a major role in the future, it's called Open Radio Access Networks, or ORAN. You might have heard this if you work in mobile networks. For sure you heard about it. And I want to explain why artificial intelligence might play a role here. So just for background, for people who are not experts, the main thing here is that we have a physical infrastructure, a mobile network, which is composed of multiple segments. So one segment is called the radio access network. So the thing that it's, let's say, closer to the users, what you are connecting, you are usually connecting to a base station. That's part of the radio access network. And we have a lot of components that go towards the mobile operator through switches, through different racks that are processing this information and bringing it to the different applications. So here, if we look at the cost of all these different pieces, because what we need more are the base stations, what we need more is what it's close to the users, and we need to deploy more and more for supporting these high data rates. There are many estimations that say that the radio access network is about 65% of the total cost of the mobile networks, right? Looking at that, what is happening is that there is what is called an ORAN alliance, which is driven by operators. Here you have a list of some of the operators supporting that. And the main idea is that they want to eliminate what they call the vendor lock-in. This means basically that so far when they develop, when they deploy a radio access network, they are kind of forced to buy all the components from this radio access network from the same vendor, because otherwise there are things that might not operate very well, right? ORAN is trying to basically define interfaces to avoid that, such that you can mix and match from different vendors. So here I have an example, the typical traditional radio access network. It's a single vendor where you have a remote unit. So this is the radio unit, the antennas that you connect to with your mobile phone. Then there is a distributed unit where most of the processing is happening closer to the users. And then a centralized unit where we have aggregation of many base stations. Here, of course, if everything is from the same vendor, what happens is that you have the radio configuration is optimized. So everything has been set properly, everything works properly, the same with the computing when you have to do processing. But of course, the competition is low and the equipment is more expensive. The idea with ORAN is to have multiple vendors providing the RU, the DU, the CU. So these are represented here by different colors. And the intention is to define interfaces that are standard such that they can talk to each other without needing to have from the same vendor. In this case, what happens, of course, is that although there is higher competition and you can have lower cost, nobody guarantees that the radio configuration or the computing configuration is optimized, right? In this case, operators could take care of this, but this is a very tedious process where many things can go wrong. And here is where I see that artificial intelligence could make a difference, right? Because what we are saying here is if we have these interfaces which are open and they define all the operations that we can do, we can look at these interfaces, we can basically test the different configurations and find which is the optimal configuration for a given time. There are many benefits of doing that. One is if there is less traffic, you can actually change the configuration to consume less power because you don't need to use the whole computing power that you might have, for example, or all the power that you have in the base stations for transmitting data because you don't have so many requirements. You can also have a hardware failure, like some servers going down and then something breaks. You will then have the same amount of computing. This will be a typical case where maybe the network breaks, but if you will detect that, you could basically still try to have a graceful degradation where you don't have these problems, and many other advantages. So here, what we are trying is with machine learning, with artificial intelligence, make use of these open interfaces such that you can optimize the radio configuration of the computing to get the best of all worlds, right? So here you can see an example of when we look at radio access networks, we have multiple base stations with different loads in terms of data rate, with different signal to noise ratio, and we can have even different computing platforms, right? Here we are considering two i7s, one with 2.6 gigahertz, one with 1.9. And then we are changing the CPU allocation, so how much computing power we have. And we are changing also the modulation encoding scheme index to see which is the best radio configuration. What we see with the different colors, throughput, yellow means we achieve the maximum throughput, dark blue means we have very low throughput, is that for different configurations with different data rate, variable SNR, with very good SNR, but variable load, we have different points where the optimal configurations in terms of CPU and radio configuration will be optimal, will be the yellow one, right? This means that we will not find one configuration which is the best in all conditions, which is what usually we have now, but we will need to be adaptive in that sense. So here, what we did was to design a system with machine learning that will learn which is this best configurations, right? So in this case, what we have is what we call the resource manager. It's brain. It's a virtualized one with artificial intelligence, where we take the different loads, the different signal-to-noise radio qualities, and this context we are feeding it to an encoder for the context, and then we have a structure of actor critic for deciding on the CPU policy and also on the radio policy. So what we are doing is we are trying different configurations for different contexts in terms of the computing control, in terms of the radio control, and then we measure the key performance indicators in terms of throughput, in terms of delay, in terms of bit-to error rate. So you can even have different basically objective functions, different objectives that you want to fulfill for some of the network slices. For some of the verticals, you might want more reliability, you might want more lower delays or better throughput. And then we compute this reward as a compilation of the different KPIs that we measure. We apply our reward function, and we give this back to brain, to this resource manager, to evaluate whether the decisions were good or bad. So we did that, and in this case with 2 virtualized base stations with different contexts. So you see that the SNR is changing, you see that the traffic load is changing. We could see how the brain policies will adapt accordingly, right? So we don't have one single solution for all possible situations where we need to do over provisioning, but we can basically change the computing configuration, the radio configuration, according to the variations that we see in signal-to-noise ratio and in traffic load. So here you see the setup of this testbed where we had different system rewards, different costs. And if you think this is still very early days, just for your information, there is already operators, large operators, in this case in Japan, like Rakuten Mobile, which is deploying Aura networks with different vendors facing some of these problems. Of course, they are not using this technology yet, but it's one of the technologies that will be enabled through these interfaces, and that hopefully we will see in the future for solving some of these issues. So this was an example for radio access networks, what is happening and how can we help with machine learning. As I was saying before, with 5G, with 6G, we are also exploring new business models. So how can we get, let's say, more motivation, more revenue in order to get better networks for everyone, so that we make the best use of the resources that are available. In this case, one of the very unpopular business models all over the world is overbooking. We chose this name for the business model a bit in a provocative manner, just to get the attention of people. What we mean by that is basically that when we have these different industry verticals with that we need to basically meet the requirements in a 5G or 6G network, they have the requirements of rate, they have the requirements of latency, they have the requirements of computing, even storage. And we can basically try to address them according to the requirements. The problem, of course, is that when new industry verticals are coming, if we don't have capacity anymore, we basically need to tell them, sorry, until we don't have a new upgrade in the network, we cannot fulfill your requirements. So the question came up with all this trend of machine learning, can we do better than that? Can we do something in order to fit as many industry verticals as possible. Of course, here overbooking came very handy, because in practice we know that if we add all these requirements, we don't have enough capacity. But if we actually look at what they are using, they are not fully using what they are requesting. So we could actually compute in real time what they're using. We could add, with some forecasting, some safety margin, but then we will have still probably capacity in some cases, depending on how critical these services are, to fit additional industry verticals. So here, this is just to illustrate that in practice, our effective capacity will be higher. So we could basically get more out of the same resources from the network. What do we need to achieve to do that? So basically, we need a physical network that is virtualized for the different verticals, where we are collecting the data from the different networks and services. We analyze this data, and then with what it's called an end-to-end orchestrator, we need to act accordingly to maximize the utilization, or even allow or not allow certain services. So in order to check how feasible this whole idea was, what we did was to look at a data set of about 20,000 base stations, 30 million individuals, and 550,000 square kilometers, where we got the data from an operator. I guess you can guess the country based on the map. So this is the data that we got from this French operator. We took the data, then divided into large cities and small cities to have different, to see whether there was different behavior depending on the size of the city. And then we took the traffic and separated it in different service types. So like if you will have a network slice, then for every network slice, maybe there is some network slice more for streaming of video, like if you're using Netflix, YouTube, Disney Plus, or some of the services, maybe for music services, others for communication services, like we are doing now video conferencing, which is more live than streaming. So we separated this in 38 service types for the different, the two different large or the smaller cities, and looked at the behavior in downlink and uplink, which were, as you can see in the pictures here, very similar. Then, since we want to do slicing, we wanted to see how we should do slicing, which will be the best way to do slices in the network. Shall we do it only on the radio access network part, which we said it was the most expensive one, or shall we also do it all the way up to the core? So we did these divisions with L1, 2, 3 to consider different aggregation points and consider two possible slices. And then for the large city, for the medium city, what we saw was which was the multiplexing efficiency if we allowed having more flexible guarantees. So if instead of guaranteeing a certain data rate in 100% of the cases, we will guarantee it only in 99% of the cases, or in 98% of the cases, how much multiplexing gain we could see. So you see that we are getting very high with already a 96% of the guaranteed time fraction. We could, so with a loss of only 4%, we could get a lot of multiplexing efficiency. And the same in terms of if we will guarantee things not only every second, but maybe every 5 minutes, every 30 minutes. So for example, if you think in IoT devices, maybe we need to send a lot of data, but I don't need to send it every millisecond or every second, but maybe 1 minute is enough. So this will allow us some flexibility in order to do some overbooking or some multiplexing. So how do we apply? This was the analysis part. Once we see that there is overbooking potential, how do we apply machine learning, artificial intelligence in order to improve things. So here you see the service demand in yellow of the traffic that we saw in one of these scenarios. And then what will be a traffic prediction with usual deep learning, where we have some errors sometimes, and sometimes it will be providing too much capacity, sometimes too little capacity, right? In practice, since we don't want that users are unhappy because their service is not running well, we actually will need to do something smarter than that, which is to have, based on this data and in this prediction, a loss function to evaluate which is the reward compared to the cost of having this overbooking in general, right? So the idea here was to see which is the traffic we have, do a prediction of how will be the traffic in the future, make our prediction, and then constantly check whether our prediction was too conservative or too aggressive. And then instead of trying to be in the middle, what we did was to basically try to be always conservative to avoid errors in the forecasting, but of course, trying to minimize the overbooking as much as possible. Here you see the result based on this machine learning solution, where we managed to be, let's say, very close to the service demand, but with our capacity forecast, we minimized a lot the errors in the forecasting in terms of we have errors, but we have pushed the errors to the positive part where the users don't notice major problems, and still we can allow multiplexing or overbook. We went even one step further than that, and we said, okay, all these reconfigurations actually have a cost. So every time we have to change the network slices because we think they will need more or less capacity, there is some component that kind of keeps constant, which is moving slower, and there are things that are moving faster, right? So we basically wanted to split that, and what we did was to, with the traffic demands that we have, we did some long-term capacity forecasting that you see here with these 3D CNNs, and also short-term demand prediction, right? Based on these two functions, we could allocate resources based on the long-term prediction, so the time windows are much higher, we don't do it so often, and analyze whether, based on the short-term prediction changes, whether it's worth actually to trigger a reconfiguration, or whether the penalty that we will pay because of the service is not that critical. We could actually live with that and have lower costs because we are not reconfiguring the network. So here you see some results with different approaches from what we call Infocom 19, Infocom 17 are different approaches from previous years. And we were basically playing with this trade-off between the reconfiguration penalty and how much cost we will have. So with this solution, of course, looking after this optimization, we could be one of the best solutions currently in the state of the art. So all of this was based on data analysis. We also have our own small mobile network. So here you can see that we have base stations, we have multiple mobile phones, an orchestrator, and a mobile core. So we tried these solutions. We basically can deploy slices on demand in the matter of seconds. And we checked in real time how much multiplexing gain we could have, which is what you see in the upper part. So just to give an impression that actually this is something that is feasible in practice, it's already being done. And we even presented this at the Mobile World Congress not so long ago. Again, I have some references there. I believe we will share the slides afterwards, so you can take a look if you like to have details on how we did these things. Then I will spend the last couple of minutes showing things where we think that artificial intelligence will be and machine learning very useful, but we don't have solutions yet, so we are working toward that. One new thing, it's called a smart or a configurable intelligent surfaces. What we mean by that is usually nowadays we consider that between a transmitter and a receiver, there is a wireless environment and we cannot do anything about that. We need to adapt to this environment. With the smart surfaces, what we are trying to do is actually to change this wireless environment in an active manner. How is this done? Basically, there are some kind of surfaces. Imagine a mirror that will reflect waves, but we can change the parameters such that they change the waves in the way that we are interested in. So here is an example of a factory of how this could help, because in a factory there is a lot of metal, so there are a lot of obstacles for the wireless signals. But we still, as we said in the beginning of the presentation, we still want to have them connected and enable remote operations, right? So here you see an example of they could be applied in train stations where we need a lot of connectivity, and there are many surfaces where we could put such kind of technology to improve this. Same as shopping centers, shopping areas, we have places where we put advertisements, and here the same, we could improve things in there. Along the road, if we want to have better and better positioning, better and better services while we are driving, is another place where usually there's infrastructure where we can put smart surfaces. And finally, even in buildings, in windows, we could think of these surfaces to actually improve the signal inside, or for privacy, preventing that the signal is moving outside. This is already happening, so these are just examples of multiple universities looking into building these smart surfaces, and a lot of European projects looking at how to enable this. As I mentioned before, ORAN is trying to configure all of these different components in an automated manner. So what is called the RAN intelligent controller. So here machine learning will fit very well. Once we put these smart surfaces also into the system, we will need to basically gently optimize all of this. Then to conclude, I have been talking about some of the disruptive technology trends moving towards 6G, but there are more. You have to think that is terahertz, there are multi-rate communications coming, there are air-to-air interface where you can adapt the modulation and coding schemes directly to the environment. Now, probably you heard about the Starlink and other high-altitude platforms where we are supposed to get a new network, a new connectivity network to be integrated with our mobile networks. And finally, we have a lot of trend towards mixed reality and augmented reality holographic communication. So with that, let's show the last video, and then we might have some questions for some time for questions. Anna, can you show the last video?
Okay, this is the big reveal.
Okay.
Right? Okay, so
well, take two, because I was slow on the draw. I didn't.
Okay.
I had my camera on the floor or something. I don't know. I lost focus. Sorry, guys. We're ready.
Right? All right. Live telepresence. You know what you can also do, instead of walking into the portal, you can materialize into the portal. Think Star Trek or any of these science fiction shows or movies that we've seen over the years. So I don't just have to walk in and walk out, I could actually materialize it, and then I could fade out. So there's a lot of really cool production effects that you could add to this to really take it to the next level. This is a basic demonstration, but we can add to that.
They want to see what happens if you walk forward, and maybe
no.
How about give a kick? Give a kick.
Okay, I'll give a kick.
Okay.
So here's a kick. Oh, threw it back out. Okay, but yeah, if I walked forward, it would just ruin it, and I would rather not.
You go out of the scene. That's why.
Yeah. You can.
Isn't it cool? You want him to do it again? Do one more walking. Walk out and then in. Wait.
Am I out of it?
Yeah, you're right. Yes. Come back.
Okay, ready?
The shadow. I mean, this is the only 4K shadow. There's nothing like this in the world. That's why it's going totally viral in a positive way. I mean, just the coverage is, and yeah. You have it? Okay. I'm gonna, if you guys stay one more minute, I'm gonna disconnecting something because I was.
Okay, so with that, I would like to conclude this presentation, and I'm ready to take any questions.
Thank you, Xavi, for this presentation. That is amazing that like this technology can we can use this technology every day, but maybe not all are so maybe we don't have this knowledge about how this technology works, or what are the limitations about this technology, and what about the next step. So I think that this presentation can show this this part of the inside of the 5G and 6G. So thank you very much for your presentation. We have one question, and we have 2 minutes. So if we have another one, we can do it. I'm going to ask you, given the rising climate change concern and the high AI and mobile network energy consumptions, it's a good idea to combine them. What do you think?
Well, I think there is no other option. So there is a lot of energy consumption given AI, and also for mobile networks. I think if we improve the operations, as I was showing before, in many cases we are using more power than necessary. In many cases we are using more servers than necessary, for example, when we are sleeping, just because there are configurations that are not needed. With neural networks, the training takes quite some energy, but actually once they get trained, we don't need to spend so much energy anymore, and then they are very efficient. So I think the answer is yes, we will need to use machine learning, but we need to basically pay a lot of attention on how we improve things such that we don't increase, and we basically meet the goals of decarbonization also with mobile networks.
Okay, perfect. So we are on time. So we are going to end this presentation with our thank you for IDOSCAT, a partner of SIDAI, and also to say thanks to all our communication team from EURECAT who made this masterclass possible. We will invite you to know more about SIDAI in our website, and to be in touch, because we are going to do some more masterclass by the end of this year, and we will continue doing this task to accelerate the adoption of this technology for all the Catalan territory. So thank you, Xavier, again for your time, and see you the next time.
Thank you very much.